In the last video, we looked at the mole method, the process by which you can move from mass of one reactant to mass of another reactant or mass of a product using molar mass and equation factors. This video, the limiting reagent, is the next logical step because in reality in chemistry, you may not know or you want to know which reagent's going to run out first because that's going to dictate how much product you form. So there's two things you have to be able to do here. You have to be able to determine what is limiting, and once you've determined what's limiting, once you've determined the limiting reagent, you use that to determine how much product gets formed. So this is a little more typical of what probably happens from a reaction point of view. Before we get into the chemistry side of things, first of all, so I do like doing the odd triathlon, and I have a sort of a makeshift tri-bike, and so I'm going to use this as an analogy because I think this is a good way to try to get a grasp on what's happening in a chemical reaction. So if we look at the components of a bike, we have a frame, we have wheels, we have aero bars, and we have a saddle or a seat. And if we put all those together, we get a bike. Now, if we then look at the floor of the bike shop and what we have at our disposal, well, that might be what you're faced with. So you have to put together your bikes. You have multiple bikes, you have multiple parts, and you're going to put all of this together. And so the question kind of becomes, well, how many bikes am I going to get out of this? Well, let's move on. So again, what do we have? We have our equation for our bike. So those are the components, the reactants. Those four components yield one bike. Now, as we know with equations, we need to make sure the equation's balanced. Well, now here's our bike equation, and it's now balanced. So one frame plus two wheels plus one aero bar plus one saddle yields one bike. So that's balanced. Now back to the bike shop floor, and you may not have been able to count everything as that quickly, but this is actually what we have on our floor. We had four frames, we had 7 wheels, we had 5 aero bars, and we had 6 seats. Now I just want to talk about the frames first, or the 4 components in blue first. And I've put these in blue for a reason, because if I look at the blue and I look at the ratio of these, it's all 1 to 1. So one frame, one aero bar, one seat make one bike. So there's the numbers. So we can, in terms of trying to find out which one's going to run out first, we can kind of exclude the aero bars and the seats, because we can tell based purely on the numbers that they're not going to run it. We're going to run out of frames before we run out of aero bars. We're going to run out of frames before we run out of seats. So in that regard, frames is kind of what we're looking at first. And then in black here I have wheels, and I've not excluded wheels because the ratio is different. We need 2 wheels to make a bike. So now I'm gonna ask myself a question. I have the components of interest, my frames and my wheels, and I'm gonna find out which one runs out first. So I'm just gonna pick one, and I'm gonna say, okay, I wanna find out how many frames I need. So how many frames do I need given my number of frames and my number of wheels? And so that becomes what I'm given, which is wheels, and I have 7 of them, multiplied by a ratio of wheels to frames. Well, I want to be left with frames, so that's 1 frame. And I want to get rid of wheels, and so in my equation that's 2 wheels. And so wheels divide out, and so it's 7 divided by 2, which is 3.5 frames. And so this question becomes, how many frames do I need? Well, I need 3.5 frames to use my wheels, to use up all wheels. Well, how many frames do I have? I have 4 frames. So I have enough. Frames are not going to run out, and so by extension, wheels must be limiting. So wheels will run out first. And so that's essentially what we do in the chemical context. So let's dive right into the chemical context. Well, actually, before we do that, I'll just briefly explain the process. So it's a limiting reagent question, okay, and it differs a little bit from a regular mole method question because you have to determine which reactant runs out first. And it's pretty straightforward. We just saw it with the bike analogy. Well, it's pretty much the same with the chemical analogy, and you've already done that. That's just a mole conversion, but we frame it as a question, and we use our two reactants to do that. I'll show that in a minute. But other than that, the process is pretty straightforward. If you look at step 1, convert a given mass into a number of moles. You've already done that, but in this case, you do it to both reactants. Step 2 is really the new step, where we ask the question, which reactant runs out first? And we carry a mole conversion to answer that question. Step 3, you've already done. Convert number of moles into moles of your given into moles of your unknown. In this case, our given is our limiting reagent. And we do that with an equation factor. It's just a mole conversion again, but now we know exactly what we want to convert. And step 4, you've already done. Convert number of moles into a mass using a molar mass. So as I said, the main difference is this step. It's a new step, and you've already done the process. So it's just making sure you remember to do that step. It is a step that is sometimes forgotten. Okay, so here's the chemical context. So we have a reaction with, again, 2.5 grams of hydrogen reacting with 27.5 grams of nitrogen. This is what makes it a limiting reagent question. We're given masses of both reactants, hence limiting reagent. And so once we've identified as limiting reagent, we just dive in and start determining masses or number of moles given our masses. So let's start. Number of moles of hydrogen. Well, mass divided by molar mass. The mass of hydrogen as given is 2.50 grams. The molar mass of hydrogen is 2.02 grams per mole. Again, you need to get that from the periodic table. And when we do that division, we get 1.238 moles of hydrogen. So there's moles of hydrogen, one reactant. Number of moles of nitrogen, our second reactant. Well, our given mass is 27.5 grams. Molar mass of nitrogen is 28.02 grams per mole. So it's going to be slightly less than 1, and in fact it is 0.981 moles of nitrogen, N2. So first step, number of moles of both reactants. The next step, as I said, now we have to determine which one of these runs out first. And so again, here's our equation. Which one's going to run out first? Well, remember what we have, moles of both. And so we ask the question, just like the bike question. The question is, which one of these runs out first? So I'm going to pick one. I'm going to pick nitrogen. Let's say I want to see how much hydrogen I need to react with all of my nitrogen. So the question is, number of moles of hydrogen needed equals number of moles of nitrogen. Well, there it is, 0.981 moles of N2 times an equation factor. Well, it's nitrogen and hydrogen being compared. I want to be left with hydrogen, so 3 moles. Hydrogen's on top. 1 mole of nitrogen is on the bottom. You should be familiar with mole ratios now, or equation factors. And so when I do that math, I get 2.943 moles of hydrogen. 2.943 moles of hydrogen. And again, the question was, how much hydrogen do I need? So I need this much, but how much do I have? Well, I have 1.238 moles. That's from step 1. That's how much I have based on the mass. So I need 2.943. I have 1.238. I don't have enough. And so hydrogen is limiting. And this is another time where I expect you to have a therefore statement. You have to include this statement. You state which one's limiting. Now let's just look at it from the other's point of view. The other question could be, how much nitrogen do I need? And so how much nitrogen, number of moles of nitrogen equals the molar amount of hydrogen, 1.238 moles H2 times an equation factor, which is going to be 1 mole nitrogen divided by 3 moles of hydrogen. Hydrogen divides out, and I get 1.238 divided by 3 equals, well, it equals 0.413 moles of nitrogen. So again, I need 0.413 moles of nitrogen, but how much do I have? Well, I have, this is how much I need again, but we have, again from part 1, 0.981 moles of nitrogen. So I need 0.413, I have 0.981, I have enough. So therefore nitrogen is not limiting, which means hydrogen is still limiting. So that's how you answer that question. But the important bit at the end of all of this is you now have your limiting reagent, hydrogen, and you know the molar amount of your limiting reagent as calculated in the first part based on a given mass, 0.1238 moles. So now we can go on to the next step, which is just finishing a mole method question given our limiting reagent. So convert the number of moles of our limiting reagent into the number of moles of our unknown. So again, our limiting reagent was hydrogen with that molar amount. So number of moles of ammonia, NH3, equals 2.943 moles of hydrogen, H2, times, we want to be left with ammonia, 2 moles of ammonia, 3 moles of hydrogen. Hydrogen divides out, and we're the molar amount of nitrogen is 1.962 moles. So now we have our molar amount of ammonia. So 1.962 moles of ammonia, and from that we can very easily determine the mass of ammonia. So there's our number of moles of ammonia again. So mass of NH3 is going to be number of moles times molar mass. Well, number of moles we just determined as 1.962 moles times the molar mass of ammonia, which is 17.04 grams per mole. Again, from the periodic table, 2 decimal places when calculating molar mass, and then we end up with 33.4 grams of ammonia produced. And so that is a limiting reagent question. So to quickly summarize, question is a limiting reagent question because you are given masses of 2 or more reactants. So if it's 2 reactants, you need to know mass. It could be more. Once identified, the process is fundamentally the same as a regular mole method question, except the given masses must be converted to number of moles. So if that's for both of them, you have to convert both masses to number of moles, and then you determine which reactant runs out first. Like I said, you ask the question, which one of these is going to run out? How much do I need of one of these? You carried a mole conversion to answer that question. But then finally, you simply convert number of moles of your limiting reagent into moles of your unknown, and moles of your unknown into a mass of your unknown, just like you did previously in the mole method question. Now, there's another sample of a limiting reagent question coming up. You can watch that if you want. There's no commentary on it, but it just does go through the process. So stay tuned if you want to watch that. Otherwise, that concludes this video.